And so hello, everyone. Welcome to the webinar. My name is Haley Carlson, and I am the program manager for the Integrated Modeling Program for Canada, or IMPC for short, as we're known. So we're a research project funded under the Global Water Futures Program, which is based at the University of Saskatchewan. And we're a large research program. Our specialty is building integrated modeling capability in major basins across Canada, particularly in light of changing cold region processes. And our flooding work, which you'll hear more about today in the webinar, is led by Drs. Elshorbagy, Papalexiou, and Coulibaly from the Universities of Saskatchewan and McMaster. So before I hand things off to Mohanad, who will be leading the presentation today, I will just note a few housekeeping things. So the webinar is being recorded and will be posted on our website, and you can see the address there on the opening slide. You can type questions in at any time during the presentation, either in the chat or the Q&A function. Just make sure that's enabled. Yes, it is. So you can see that. I'm sure everyone is extremely familiar with Zoom at this point in a global pandemic, but if you're not, you can hover your mouse over the bottom of the screen, and a little Q&A panel or chat panel will pop up, and that's where you can type your questions. I will be addressing those verbally to panelists after the presentation has completed, and we have a period of time for some questions and answers. And then with that, I will introduce Mohanad Zaghloul, a PhD candidate at the University of Saskatchewan. Mohanad will be speaking about his research contributing to improved flood prediction efforts in the Canadian prairies. So with that, Mohanad, please take it away.
Thank you, Haley. As Haley said, I'm a PhD student at the University of Saskatchewan, and my supervisors are Dr. Amin Elshorbagy and Dr. Simon Papalexiou. But before we start, I would like to highlight that as we gather here today, we acknowledge we are on Treaty 6 territory and the homeland of the Métis. We pay our respect to the First Nations and Métis ancestors of this place and reaffirm our relationship with one another. I also want to acknowledge the great effort and continued support from Dr. Amin Elshorbagy and Dr. Simon Papalexiou while conducting the research presented in this webinar. So, as I live in Canada, specifically in the Canadian prairies, when I hear someone saying the spring is approaching, I start worrying about potential spring floods and flood damages that are about to happen. However, we could increase our chances to reduce flood damages and set efficient flood protection measures if we could learn from the past historical events how spring floods are generated. So in this webinar, I will present some of the ongoing research in the IMPC and GWF towards characterizing the various ways in which spring floods are generated in the Canadian prairies. I'm showing here a map of Canada. I'm highlighting also the provinces of Alberta, Saskatchewan, and Manitoba. And the region of interest is the Canadian prairies that extends across these three provinces. And it consists of about 500,000 square kilometers of land. And this region is characterized as a cold region with generally undulating and flat topography. The climate and topography of this region plays a major role in making its spring floods unpredictable. These are also three examples of the floods of the Canadian prairies. A flood in 1997 in Manitoba, 2011 across Saskatchewan and Manitoba, and floods at several places in Alberta in 2013. But I want to highlight that flood that happened in 2013 and inundated the downtown of Calgary with damage estimate over 6 billion Canadian dollars. And that flood that inundated the downtown of Calgary only had approximately 1 in 40 years return period, as estimated by Pomeroy and others in 2016. So, in literature, various hydroclimatic bathing conditions have been investigated to know the cause of some of the prairie floods. So let's have a look at these hydroclimatic conditions. An example of these conditions is the rain over snow, which is infrequent, but when it occurs, it plays an important role in generating spring floods. An example that was discussed by Stadnik and others in 2016 about the flood that happened in 2011 in Manitoba was presented, and they showed that that flood was triggered by excessive rain over snow when the bathing conditions was wet. This highlights the importance of considering the wetness of the basin as well. Another condition is the availability of the snowpack, accounting for the accumulated snow that falls over winter and the possible losses that could occur from it. There could be a thick layer of snowpack with high snow water equivalence or just a thin layer prior to the spring flood. Also, the midwinter melts could play an important role in depleting the snow water equivalence of the accumulated snow cover, which usually occurs in the southwestern region of Alberta due to a warm wind coming from the Rocky Mountains, typically called the Chinooks. The midwinter melts could also affect the soil moisture conditions and limit the infiltration of runoff during the flood generation process. Also, the state of the available snowpack in terms of being ready to melt and start contributing to generate spring runoff is an important aspect. And when the snowpack reaches its melting phase, it's important to consider its melting progression, which is controlled by the rate of energy needed for melting, by the rate of change in the energy needed for melting. So since these bathing conditions could describe the cause of spring floods, they could also be investigated along with the historical spring floods to understand basins' flood responses to different bathing conditions. However, this approach could be challenging in the Canadian prairies because the interaction among bathing conditions occurs in numerous forms, and each form could lead to a different spring flood generation mechanism. In literature, some studies attempted to classify floods without considering the interaction between the hydroclimatic conditions. For example, when the conditions during just a few days prior to a flood are only considered, then the rain over snow might be thought as the main cause of spring floods without considering the possible contribution of snowmelt. That could be affecting the soil moisture conditions and controlling the impact of the rain over snow. This takes us to the objectives of our investigation, which was characterizing the various spring flood generation mechanisms in the Canadian prairies in a comprehensive way that considers the possible interactions between the various hydroclimatic conditions of the basin, and then use the characterization of the past historical floods to enhance our knowledge of how spring floods are generated in the Canadian prairies as well. And we followed three steps to achieve these observations. First, we identify the bathing conditions associated with historical spring floods. After that, we established a statistical model named the Copula to simulate the relation between the bathing conditions and the spring floods. The Copula simulates this relation at a statistical correlation structure. And then finally, we use the established Copula to explore the flood response to different bathing conditions. So the first and initial step in this analysis was to sample the historical spring floods. And the historical daily stream flow records were obtained for that reason from 1979 to 2018 from the Hydrometric Database of Environment and Climate Change Canada. The stream flow data at all of the prairie stations were investigated, and stations with auspicious trend changes or short records or heavy regulations were excluded to ensure the quality of this analysis. The screening resulted in 84 basins in the Canadian prairies, and those are the basins I'm showing in this figure, distributed across the prairie region. So at each basin, at each basin of these 84, spring floods were sampled from the daily stream flow records in each year. For example, this is a daily stream flow observed at one basin in 1997. The x-axis shows the dates during this year, and the y-axis shows the magnitude of the observed stream flow. The maximum observed event of this year occurred on April. Its magnitude is sampled at the spring flood of this year, 1997, together with its date of occurrence, because the date of the flood plays an important role in the next steps. So, since early spring floods could also occur in the Canadian prairies, the floods that occurred in the period from the 1st of January to the end of May 31 are considered as spring floods. And so, A spring flood is sampled from each year at the maximum daily stream flow in this period, with the condition that the sampled spring flood is not exceeded during the rest of the year. So to define the conditions that contributed to the generation of this spring flood, we considered the hydroclimatic conditions prior to the flood date. And those hydroclimatic conditions, as we discussed earlier, are the availability of snowpack and its snow water equivalents, the presence of rain over snow and its magnitude, the state of the land depressions, whether they are empty or filled with water and snow, the soil moisture conditions, the melting phase, the snow melt progression when the snowpack reaches its melting phase, and the possible midwinter melts. And to account for these hydroclimatic conditions, we defined 7 variables. The way that each variable was defined will be presented in the next slide, but let me show you here what each variable accounts for in terms of the hydroclimatic conditions. So the snow is our first variable. We called it snow, and it accounts for the availability of snowpack. The second variable, precipitation, is more comprehensive than the snow, and it accounts for availability of snowpack, the rain over snow, and the state of the land depressions during the winter. The rain is the third variable, and it accounts for the rain over snow, the land depression state, and the soil moisture conditions. Both the variable number 4 and 5, API and API2, which are abbreviated from antecedent precipitation indices, accounts for the state of the land depressions and the soil moisture conditions, but before freezing. The melt here also accounts for the snow melt progression and the melting phases. And the last variable is called SPT, abbreviated from snowpack temperature, and it just accounts for the how cold was the winter. And that could refer to the presence of any midwinter melts, which would influence the availability of snowpack. So back to our example, this is the spring flood of the year 1997. And to investigate the conditions prior to this flood, we extended that period to the previous summer, fall, and winter. So the first variable that we have is the snow, and it's estimated at the accumulated amount of snowfall that falls from the 1st of October to the date of the spring flood. And that snowfall is estimated from the precipitation records, with the assumption that snowfall occurs when the temperature is below 0 or equal to 0. The second variable, which is more comprehensive than the snow, is the precipitation. And it's more comprehensive because it considers both the snowfall and the rainfall together. So, and it also is estimated as the accumulated amount of precipitation from the 1st of October to the date of the spring flood. The third variable that we have is the rain, but to estimate this variable, we need to define a date from the temperature first. So I'm here plotting temperature time series of that period, and the date when the temperature first drops below 0 is that date of interest that we are looking for. So the rain can be estimated as accumulated rainfall from the date when the temperature first drops below 0 to the date of the spring flood. And it's clear from this variable that the contribution of the rain over snow in this period was not present in the contribution to this spring flood, since there is a limited amount or even no amount of rainfall that occurred prior to the occurrence of the spring flood. So we can imply from that that the snow was the main contributing factor for the generation of this flood. So let's look at the next variable, the API, antecedent precipitation index. And it's also estimated from the rainfall, but this variable is meant to account for the soil moisture conditions before freezing. So it's estimated at the accumulated rainfall in the 30 days period prior to the date of the first drop in temperature. But as you see here, there could be some events, important events, that are not accounted for in API, such as this one, just before the 30 days. So we defined another antecedent precipitation index and called it API2, but it's more general because it would consider all the precipitation or the rainfall that occurred from the 1st of June to the date of the first drop in temperature. Indeed, a portion of API2 will be lost as evapotranspiration, infiltration to the groundwater, or exit the system as summer stream flow. However, it still provides a general overview of the basin wetness during the previous summer. The next variable is SPT, which accounts for snowpack temperature, and it's used to and it's estimated also from the average daily temperature records as accumulated temperature records from the first temperature drop below zero up to the date of the spring flood. And this accumulated value is then multiplied by -1 to make the interpretation of SPT easier. So higher SPT values means colder winter with a well-preserved snowpack, and lower SPT values means warmer winters with less preserved snowpack. The last variable that we have is called the melt, and it's also estimated from the daily average temperatures during this period. So this melt will be focusing on that short period prior to the occurrence of the spring flood. So let me zoom in to that period, and as we see here, there is an increasing trend that's very clear that the temperature was increasing prior to the date of the spring flood, which typically leads us to think about that the snow was happening, snow melting was occurring here. So to capture this rate of increase in the temperature, we define the date when the run of days with positive temperature is greater than the run of days with negative temperature, this date. And the temperature records between this date and the date of the spring flood is used. So we fit a linear model to these temperature records, and the slope of this segment is the value of that variable, the melt. So at any basin, we could have different years, and each year would have a spring flood. So for example, year 1 would have a value for its spring flood, and other 7 values sampled in that way that we just defined. And that could happen next year and so on. So we sampled all the spring floods and its associated 7 variables that describe the bathing conditions that led to these spring floods. But the relation between the spring floods and their associated bathing conditions is described in terms of their probabilities. So it's essential it's an essential step to estimate the probabilities of the observed variables. The probability of the spring flood, for example, was estimated using the traditional Weibull formula, which says that the non-exceedance probability of any record is equal to the rank of this record divided by the sample size plus 1. And however, the empirical non-exceedance probability of each of the 7 variables, the snow, precipitation, rain, up to the SPT, are estimated in a more advanced way to overcome a statistical dilemma. If anyone is interested in knowing about this, we can discuss it at the end of the presentation. Now we have the 7 variables corresponding to each spring flood in each of the 84 prairie basins. That sums up to 2,279 spring floods in the Canadian prairies. For simplicity, let me show you the greatest spring flood observed in each basin, and that would reduce the sum to only 84 spring floods across the prairies. So at each of the 84 basins that we are investigating, we only selected the greatest flood that was observed at each basin. And the time when these greatest observed spring floods occurred is described by this bar chart. For example, in 1997, there were 21 basins that reached their greatest observed spring floods. And also in the year of 2011, only 20 basins reached their maximum observed spring floods. So the greatest observed spring floods, regardless of the time of its occurrence, in each basin was investigated in the next slides. So at each basin, for example, in the first basin, we would go sample the greatest observed spring flood in that basin, and link it with its associated bathing conditions using those 7 variables. And this combination is referred to as spring flood generation mechanism of basin number 1. We did the same thing for the second basin and obtained the spring flood generation mechanism of the second basin. And we did the same for all of the 84 basins. So each spring flood generation mechanism consists of one spring flood and its associated 7 variables. So if you want to describe those the mechanism of the greatest observed spring floods at the 84 basins, we would plot this table with basin number on the y-axis and those variables on the x-axis. And that leads us to this figure. So here on the y-axis, we have the basin numbers, 84 basins. Each row in this table describes the flood generation mechanism of one basin. And on the x-axis, we are showing the spring flood and its associated 7 variables, starting from the snow to the SPT. So if we look at the top basin here at the top, we will see that the range of colors here are changing. And these colors, in fact, describes the non-exceedance probabilities of each record. If the color is red, it means that it has a high non-exceedance probability, which indicates that the value of this color is high compared to its peers in its basin. And that it's naturally to see that the spring flood values here are all red because we are plotting the mechanisms of the greatest observed spring floods. So for example, if we look at the mechanism at the top of basin number 84, it's going to have a red color for the spring flood because this is the greatest observed spring flood in that basin. Following the same concept, if we look at the snow, its color is blue at the top here for that basin. And that means that the snow was actually low compared to its peers in that basin. On the contrary, if we look at the rain and go to this top basin, we will see that it's kind of having a high value towards the red color. And that means that the rain was probably the main contributor to the generation of the flood in basin number 84. But what I want to tell you from this figure is that the random pattern that we see from this 84 flood generation mechanisms implies numerous ways of interaction among the bathing conditions that work together to generate the spring flood. And the greatest observed spring floods could be generated with a combination of non-extreme basins, and that's clear here because these are the greatest observed spring floods. They are all red, and they sometimes can occur when the basin conditions are moderate to low. And that implies an amplifying effect on the spring floods. And that effect is caused by the interaction between the bathing conditions. So this interaction should be investigated along with its effect on the spring floods. The historical generation mechanisms observed in each basin could be used to establish a multivariate probability distribution that simulates the interaction between the bathing conditions and the spring floods. So a copula is simply a multivariate distribution with a better handling of its marginals. And there are numerous copulas in literature, but the T copula is the most suitable for this analysis. So here we are describing the interaction between the bathing conditions and the spring floods using the T copula in an 8-dimensional framework to describe the correlation structure between the spring flood, the snow, precipitation, rain, and the rest of the bathing conditions. And to simplify that, I'm going to show you only a demonstrative example of T copula describing the correlation structure between the spring flood and the snow only at that basin highlighted in the middle of the prairies. And the area of that basin is approximately 860 square kilometers, and it's located at about 150 kilometers south-southwest of Saskatoon, and it contributes to the South Saskatchewan River. So in this simplified example, I will highlight the importance of simulating the correlation structure between spring floods and bathing conditions, which is going to be only snow in this example. As illustrated in this figure, x-axis denotes the non-exceedance probability of spring floods, and the y-axis here denotes the non-exceedance probability of snow, while the z-axis denotes how likely any pair of x and y could occur together. So if the point that is shared between x and y is high on this surface, it means that they are more likely to occur together. If it's at the bottom, it means they are less likely to occur together. So at any pairs, if we go on x and y and see that they share this point, for example, and that point is the highest, like here, for example, on the top of the curve, then this is the most probable combination of spring flood and snow to occur together. So what is that useful for? The point here is that the correlation structure can tell us what is the spring flood that is most likely to occur with, for example, a 40-year snow event. So if we fix the snow events at 40-year return period, that would be equivalent to a probability of non-exceedance of 0.975. And that we would enter then this axis with 0.975 with the probability of the 40-year snow. And we would keep searching for the combinations with the spring flood probabilities. That would provide us with the highest likelihood. That would describe the combination that are most likely to occur together. So we could go to the next step and obtain the probability of that pairs. So the probability is 0.98 of the spring flood, and that's the probability that's most likely to occur with a probability of snow equal to 0.975. And that probability of the spring flood is equivalent to a 50-year return period of spring floods. The third step is to convert this return period to its quantity, to quantify the amount of the spring flood that is most likely to occur when the snow is equivalent to 40 years. And that flood frequency analysis is conducted using the commonly used distribution, the JEV distribution. However, the JEV distribution, generalized extreme value distribution, could have a serious limitations. So we investigated a more reliable distribution, which is the bar type 3. Which is the bar type 3 distribution, and proved that it overcomes those limitations in a published manuscript in the Journal of Advances in Water Resources. However, the fitting of bar type 3 distribution is a challenging process, and many could find it difficult to implement. So we developed an R package, which is the ELMO fit, called ELMO fit. And that package facilitates the use of bar type 3 distribution and facilitates the use of the bar type 3 distribution. And this package was published on CRAN, which is a free access archive for R packages. Anybody can access now. We will present examples of the various applications of this package in a conference presentation at EGO 21 on this April. So you may attend if that captures your interest. So back to our example, we fitted the distribution, the bar type 3 distribution, to the observed spring floods, and went to investigate what if the probability is 0.958, what is the corresponding quantity of spring flood? And that was equal to 21.3 cubic meters per second. That means from the correlation structure that we established between the spring floods and the snow, we can imply that a spring flood of 21.3 cubic meters per second is the most likely to occur with a 1 in 40 years return period of snow events in that basin. So this example was applied in an 8-dimensional framework when the bathing conditions was described by 7 variables instead of only the snow. And I'm here going to show you an example of the results at one basin. So For example, the spring flood that occurred in 1997, here is this on the x-axis, we are plotting the spring flood along with the 7 variables. And on the y-axis, we are plotting the return period of those values. So the black line on the figure shows the observed event, which is sampled from the basin during the year of 1997. And those group of values describe the bathing conditions, the snow API up to SPT. So we went to the fitted copula and fixed the bathing conditions and let the copula estimate the most likely spring flood that would occur with these bathing conditions. And we found that the copula underestimates the return period of the flood of 1997 by 5 years. So we did the same thing in the flood, for the flood of 2006. And we found a great match between the copula expectation and the observed spring flood. Both of them obtained the same return spring flood with the same return period. And if we compare the mechanisms here, by the way, we can see, like we can interpret the main contributor to the generation of the observed spring flood. For example, in the flood of 1997, it's clear that the snow was higher than the rain, for example. And it's clear also that SPT value is very high, which indicates that the winter was very cold before the occurrence of the spring flood. And the cold winter here implied that the snow that fell over the winter was well preserved until the time of melt that generated the spring flood. We can also see some contribution coming from the precipitation here and low contribution coming from the rain over snow. So this flood was probably caused by snow melt. And in the flood of 2006 here, when we look at the mechanism, we can see that the rain actually had a recognizable contribution, the rain over snow, and also the snow value that fell over the winter was also recognized. So probably here in this basin, in the year of 2006, both the snow melt and rain over snow interacted together to the generation of the spring flood. And we can also see the previous summer was pretty wet compared to, for example, the flood of 1997. But anyway, when we implemented this approach to other years like 1994 and 2015, the copula was able to capture the spring flood with the same return period. So to sum up these 4 years, for the years 1994, 1997, 2006, and 2015, the bars here describe the return period of the observed floods for those bars. And the black dots on each bar describe the return period of the most likely flood, spring flood that would occur based on the prediction of the copula. And as you see here, there is the copula shows promising results in describing the relation between the bathing conditions and the spring floods of various return periods. It can capture the correct return periods at numerous years. So, since the fitted copula could describe the interaction between the bathing conditions and the historical spring flood, we used the copula to investigate the spring floods of 50 years and 100 years return periods. So this figure shows 2 events generated from the copula. And here event 1 is presented with a solid line and event 2 is presented with a dotted line, and both of them would lead to a flood equivalent to 50-year return period. They are most likely to lead to this flood based on the copula. But the interesting point here is that there is a compensating effect due to the interaction of the bathing conditions. For example, event 1 has a significantly lower snow quantity compared to event 2. However, if we consider the rain as well, we will find that that was compensated by the rain over snow. And if we also consider the API, we will see that event 1 occurred when the wetness of the basin of the soil, when the soil moisture before freezing was much higher than that of the event 2. So when even with a snow amount, even with a low amount of snow, if a rapid melt occurs over a wet basin with some rain over snow, it would result in, it's more likely to result in a 50-year spring flood. We did the same thing for the 100-year spring floods in that basin. We let the Copula set the basin conditions that are likely to generate a spring flood with 100-year return period. And we also noticed that compensating effect, especially between the snow and the rain over snow. So this leads us to the conclusion that different spring flood generation mechanisms could trigger the same spring floods. And extreme spring flood could be generated from a combination of non-extreme bathing conditions, like the example when the snow was not significant, and even so with other combination, by considering the other bathing conditions, they could amplify the power of that limited snow to generate a strong flood. And the third one is the investigated bathing conditions should all be considered to characterize spring flood generation mechanisms in the Canadian prairies. We can't look only at the snow and decide what is the predicted spring flood. We should consider all of the bathing conditions. So to sum up all these, there are numerous possibilities of interaction among the basin's hydroclimatic conditions in the Canadian prairies. And there is no dominant process that controls the generation of spring floods in this region. And also extreme spring floods could be generated with a combination of non-extreme bathing conditions. And there are also interaction among the bathing conditions that could have a magnification rule on generating extreme spring floods, and the multivariate Copula is a promising tool for characterizing the numerous flood generation mechanisms in the Canadian prairies. And understanding the system is an initial and essential step towards predicting it. So that's what we are heading to. So thank you for your patience, and I think we can start the discussion period now. Thank you.
Thanks, Mohanad. Sorry, my video was bugging there. Thanks so much for the presentation. It's so good to hear all of the progress that's been made over the past year, because it's been a while since I've spoken to you. Very interesting work. I'm just going to start you off with a question that I had posed a little while ago. So the question was, how do you anticipate your study results will help in improving flood prediction or flood mapping efforts in Saskatchewan?
Okay, so what we are doing now is understanding the flood mechanisms. So once we understand how the system works, this will enormously help us to be able to predict the system. At this point, we can only describe how the system works. At this point, we still can't predict when the system, when the spring floods are going to happen. Exactly, because the way that the bathing conditions are accounted for is considering the date when the spring floods occurs. So we can't use these variables with their current definition to predict the date of the spring flood. But most importantly, we can at least now understand how exactly any basin would work in generating their spring floods. So there's still some future work that needs to be done before we can be able to predict the time of the spring floods. And also in terms of flood mapping, understanding how the system works can also maybe I guess, contribute to maybe we can enhance our flood mapping based on the bathing conditions. I think if Professor Amin can contribute to this point, it would be nice as well.
Well, which point exactly, Mohanad, of what you refer to?
The point about the flood mapping. Like, how can we use the bathing conditions to account or enhance our flood mapping? In my opinion, we can use the bathing conditions. Like, for example, if there are some years with missing stream flows, or for example, if we know only the bathing conditions and we want to, based on the correlation structure that we built between the bathing conditions and the spring floods, we can use these bathing conditions to quantify the amount of the spring floods. And then we can, based on that quantified amount, we can like do the flood mapping, even without having stream flow records. Like, we can build our own stream flow records based on.
Thank you, Mohanad. I think this work can mainly be used early in the spring to highlight the conditions of the basin, to highlight which one of the 7 variables, or if all of them are at high values or moderate values or low values, then we can have some sort of an assessment of what could be the triggering mechanisms. And this would also tell us that which basins are more likely to have higher floods than others. And in terms of assessment of what would be the contributions, which basins are at higher risk of flooding and so on. But to do any kind of prediction, we need to restructure a little bit the way we are constructing the model, so that we can provide a prediction of the magnitude of the flood. I don't think in this work we are heading at all towards the timing of the flood, because the timing is a forecasting issue, and we have not constructed our methodology to do that. But in terms of magnitude of the flood, I think we can do a little bit of work to move towards this issue, and at least highlight what is a generating mechanism and how this is different across the different basins in the prairies. Thank you.
Great, thank you. I'm keeping up because I'm trying to type all of the answers at the same time as you speak. So sorry for the delay in unmuting there. We do have a question here from Tyler Black, who is asking, what was the deciding factor in defining API 2 as going back to June 1st? Did you experiment with other time intervals for this?
So let me go to that slide. When we define the API 2. So here API 2 accounts, as we said, for the total rainfall that occurred from June 1st to the time when the temperature drops below 0. And the point of doing that is to account for the bathing conditions during the previous summer. So also the precipitation, also the soil moisture conditions could be only before freezing, could be well described by the API, but some major and important precipitation events or rainfall events that could occur before this period, just even before this period, could not be captured and accounted for. So, for example, these 30 days describe a small amount of rainfall which would influence the soil moisture conditions before the time when the soil freezes up. So at the time when the spring flood occurs and the soil starts thawing, the soil moisture conditions would still be the same as before freezing. So that would influence how the amount of infiltration that could happen and mitigate the magnitude of the spring flood. So since the question is on API.
If I may intervene here, Mohanad, just to give maybe a straightforward answer to the question, we have not experimented much as far as I know, and Mohanad can correct me for this, with the date, whether it is June 1st, whether it is June 15, or if it is May 15. I think what we wanted to capture in API 2 is just the most of the summer season or the entire summer season, and try to assess the wetness of the basin throughout the entire season before freezing. So that was the idea of picking this date, exactly as it was for picking 30 days in advance of freezing. This again was an assessment of how much will be the wetness of the basin that perhaps is still there, was not lost due to evapotranspiration, because this was the end of the summer, this was the fall season when the plants are dormant, so perhaps 30 days is good enough. We didn't do sensitivity analysis in terms of how about 35 days, how about 40 days. We did not do that. I think these are niceties that can be done if deemed necessary. Thank you.
Thank you.
Great. I'm going to ask a related question that Curtis has followed up with here. He asked, was there any thought to using SPEI as your API variable, using temperature data as well to account for evapotranspiration? We found that in the Souris Basin, that is a very good indicator for conditions at freeze up.
Yeah, so you're saying using SPT to account for
SPEI.
Yes, so I think what Curtis is referring to is that you already considered the amount of rain that came over the summer. How about looking at the evapotranspiration that also happened during the summer, so that you can assess how much of it is left? So we have not done this. Are those 7 variables that we used a really exhaustive list of variables? We don't think so. I think we can come up with a much longer list of variables. At this point in time, we assessed that those 7 variables might be enough to capture, because I need to remind everybody here with something, that we are not trying to really predict a daily stream flow. We are trying to predict the highest flow value, which is the peak, right? The flood. So there are many variables like radiations, like evapotranspiration, as Curtis is saying, that will play a major role in how much runoff is happening. But to pick that single value, which is the peak, it is our assessment that those 7 variables are playing the most significant role. But I'm sure experimenting with so many other things could maybe change our assessment or improve even our results. But it's a good and valid point. Thank you, Curtis.
Okay, great. Another question we got from Andre was, do you see a risk of overfitting, and what do you do to mitigate that?
Okay, so the risk of overfitting, up to my knowledge, is when we fit a model that have excessive amount of parameters. So this is not the case in our model. So what we are doing is we are trying to capture the correlation structure that describes best the observations based on the T-Copula. And the T-Copula describes this correlation structure by rebuilding the same, by reusing the same correlation matrix between the variables. So what we do simply is that we get the correlation matrix between the variables, we use it as the parameters of the T-Copula, and then we use that copula to describe or restructure the correlation structure between those variables. So I don't see any risk of overfitting
in our approach. Great. Okay, this is another question from Curtis. He has a lot of questions about this work, some of it's been somewhat answered, but I'm going to pose it anyways in case you guys want to follow up with any additional comments. He asked, he's wondering if has been any thought to taking a similar approach, but using runoff volume rather than peak flow, as the volume is often of more interest in terms of water supply.
We haven't considered the runoff volume yet. Maybe in the future we could consider that. But at this point of the analysis, we only considered the peaks. We didn't consider the volumes.
Yeah, I think the issue of the runoff volume could be interesting, and I would like to have some discussion with Curtis on this issue, because to talk about the runoff volume, we need to identify a window for the volume. So is it the spring runoff volume? Is it longer than this? So that can be interesting point, because based on the window of that runoff volume, we need to restructure our input variables. But this would be for sure very useful to identify the volume, so that this work can contribute also to water management, not only flood assessment issues. Thank you for that.
Okay, great. I'll ask another question here. So what are the next steps for your team that you're sort of seeing over the next year? Do you have any manuscripts on the way, or some data publications that you're considering moving forward with?
Yes, so there is a coming manuscript on this analysis and the way of characterizing the bathing conditions. After that, we might use this descriptive way for describing the bathing conditions in the regional flood frequency analysis for describing the similarity between the different basins, and that would have a significant role in enhancing the pooling that is being done in the regional flood frequency analysis.
We had a follow-up question from Andre. If you recall, he asked the question about overfitting, and he followed up with, are not all elements of the correlation matrix effectively free parameters? I'm not familiar with T-copulas. Did you do cross-validation?
I don't think we did that.
Yeah, we have not done cross-validation. I think what the question is referring to is perhaps the issue of splitting data to what is called the calibration and validation kind of thing. But the cross-validation will require three split samples. So we have not done this, as it is really uncommon approach. It's more common in machine learning and in data-driven modeling. It's less common in a statistical analysis. But I don't know if Simon has a comment on this issue. If we need to do cross-validation here, or
yeah, I was just about to comment on that too. I just unmuted myself. No, we didn't do cross-validation, and this is right. These are free parameters, but don't forget that this is an approach and a model to understand and explain things. It wouldn't work like this. It needs a different formulation almost of all of the variables to try to make this operational in a forecasting manner. Because here, don't forget that we know when the spring flood happened. So this means we're investigating the correlations with potential variables that have affected this peak. In reality, you don't know that. So the formulation of the definition of the variables has to be very different and in a very fixed way. Probably it needs a multivariate model that uses the Copula, and it will run day by day, but the variables will be defined in a fixed way. Let's say the previous 30 days of rain, 2 days before, the 2 days before, I don't know. This needs really a lot of investigation, and I remember in the beginning, we have done some of these tests actually, because the key concept here is it possible to find the period, the time window that is more strongly correlated with the peak? And then you set this in a multivariate model framework, in a, in another regressive framework, and to exploit this. So we tried what is the correlation with 30 days before the peak, 2 months before the peak. So it needs, I would say, a brute force attack method to try to identify if such windows actually can be identified and offer more. But I repeat, this framework is to understand and not to be used for forecasting. The formulations is going to be very different.
Yeah. I also want to add something that the fitting that we are doing is done at each basin specifically. So at each basin, we fit the copula, the T-copula, to describe the correlation structure between the bathing conditions of that specific basin and the spring floods of that specific basin. So a limitation that we would face if we try to make cross-correlation and splitting our data into 2 groups or 3 groups is the limitation caused by this range of records that we have. As you know, that since our variables are estimated based on the precipitation and temperature, these are not available data for long periods of time. And since we are working on the annual scale, like 1 spring flood for each year, so we have a limited number of mechanisms that we are trying to describe. So if we split our mechanisms, the number of mechanisms in each group would be very limited. That would significantly affect the fitting of the T-copula. Thank you.
Okay, great. I don't see any new questions, and we're actually pretty close to the hour here. So I'm going to call it to a close today. And it sounds like there may be some interesting follow-up with the Water Security Agency on potential applications of this work. So that's exciting. And I want to extend my sincere thanks to Mohanad, Amin, and Simon for joining us today and sharing progress on your work with us. I did provide a couple of links to your manuscript and the package that you published on CRAN as well. Did you have any final things you wanted to add to the audience at all, or should we call it for a close today?
I would like to thank everyone for attending, and looking forward for further discussions in the future. Great.
Okay, thanks so much. And thank you everyone who attended and spent the hour with us today. This is being recorded, as I mentioned, and will be posted on our website in the next few days here. And with that, have a good rest of the day, everyone. Bye-bye.
Thank you. Thanks, Haley.